Hello everyone, if everyone can have a seat so we can start the session. For the one quick, we'll have three presentations. The first one will be delivered by CJ, who is a hybrid engineer with rich domain expertise in reservoir, production, and commercial industrial facility engineering systems. He earned his bachelor's degree in electronics engineering and a master's degree in petroleum engineering from the University of Southern California. He has worked for ExxonMobil, Area Energy, and technology startups in Silicon Beach. And presently, he is the principal and energy data scientist at hybriData, a startup in Los Angeles, California, where they leverage big data, IIoT, robotics, and machine learning and artificial intelligence to solve complex real-world energy problems. Please give him a warm welcome.
Oh, excuse me. I think I can use this, right? Okay, it's working. Thanks. Hi, good day, everyone. Thank you all for being out here for my talk today. So my talk is about how we use deep learning and computer vision techniques for corrosion risk assessment. I didn't do the work alone, so I did it with my co-author, Chuma Jamuda. Fortunately, he's present here, with me presenting it. He's right over there, and he works with, Saudi Aramco. I am CJ Jamuda, like, the earlier presenter alluded. In today's context, you can call it like the founder of hybriData, but I like to, think of myself as the principal engineer and scientist at hybriData. So for this talk, I'll just give you guys a feel of, the two papers we presented on this topic. The first paper was an SP 1900-363 paper, MS paper in California on the same topic. Then based on the results we obtained from, using deep learning and computer vision techniques for the first paper, we also published another new paper too. Yeah. So without much further ado, I'll just give you guys a feel of, what my talk today will be about. First of all, I'll start up giving you guys a feel of the challenges and benefits in terms of working with computer vision and deep learning models for corrosion risk assessment. Next thing I'll talk about, the corrosion types we considered when, building these models. Then finally, I'll give you guys, I can go as high level as possible, as low level as possible, depending on time. But I'll talk about, the key, techniques in computer vision and deep learning we use in achieving this. Then share, some of the results with every one of you. Then, share conclusion and possible improvements as I see in this domain. So in terms of the challenges, I believe like a lot of us, know about it. If you don't have a big research facility like the PRCI folks, it's tough for you to get, a good amount of data. So for us, the key challenge we faced when building this model was, the limited amount of data for the different corrosion types we were considering. Also, even when you get the data too, the challenge too is the quality of the data, because depending on how the resolution of the data you're using in building those models, it affects, your eventual prediction. So those are some of the challenges we face. Then model training. So in terms of model training, even if you're using like a cloud infrastructure like we use, you're storing it in something like what they call object storage, what they call S3 buckets to always read the data, load the data, and train your models. You face like a lot of, in terms of the time it takes. And also the inference time, depending on the computer vision techniques you deploy or you integrate into your model, your inference time, like your time after you've predicted, after you've trained your model, your time of response, it depends on, you get, it's a lot challenging, especially if you're doing like research, you want, it to be as fast in terms of iteration. So talking about the benefits, not just the benefits, I can't just overstate it. The last, all the two speakers earlier, they spoke about, how data is really valuable. One key area we see in, using deep learning and corrosion, using deep learning and computer vision techniques for corrosion risk assessment is any form of subjectivity that we normally use in, our facilities to determine the corrosion defects will be, eliminated. Also, it will lead to a lot more objective risk assessment in terms of you can grade different cases and different scenarios. Another benefit we see is that, in terms of the time for you to act, in terms of time for you to implement your corrosion risk assessment strategy, it will be reduced because one is what you're, not just only are you inspecting to go back, to analyze the data, then come up with what your implementation strategy is, but you can actually implement, analyze it, and execute it, which also leads to the third benefit of reduced costs. So prior to working on this on board of the papers, so we considered several NACE corrosion types. So I believe like a lot of us in the room are familiar with the group 1, group 2, group 3 corrosion types. But what we're trying to point out from this slide is just giving you a sense of feel that the group 1 in particular, you may be able to spot those corrosion types from ordinary visual inspection. Then group 2, you need supplementary more amount of detailed data for you to be able to identify that corrosion defect. Also for the group 3, you require more advanced sensor equipment or sensors to be able to detect what kind of corrosion defects and even more advanced analytics. So just, capturing all of that, the 3 NACE corrosion types. So for the 2 papers, the first paper in 2018 that we published and presented in California, and the last paper this year we published as well. These are the different corrosion types we considered. Under the group 1, we considered uniform corrosion, pitting corrosion, galvanic corrosion, group 2, intergranular, then group 3, stress corrosion, cracking. So after we identify what type of corrosions we wanted to identify, the next step for us was, hey, how can we not just only detecting the corrosion type, but how can we scale it? This object detection and localization and instance segmentation, those are more advanced levels. It's not like, corrosion defects determination had not been in existence before deep learning and computer vision. It has always been there, but previously it's a lot more customized or manual, would I put it manual classification. So basically, it's just almost like you're building a custom solution for a custom problem. But with the advent of computer vision, with the advent of deep learning, you can now be able to do a lot of things. So for us, we consider 2 types of computer vision tasks. One is object detection and localization. So just kind of a quick question here. Has any of us here trained a neural network model before? Training, writing the codes from scratch with Python or, okay. Because what I want to really break it down is this. So there's a layer above this other computer vision techniques I'm putting out here. And I'm not trying to, I would like to, just explain it better. So in computer vision, the first step is always classification. So let's say I take a picture of everyone here, right? The classification will just say, this is a human, right? But for object detection, you can say, okay, there are 10 humans here, right? So in this case, object detection and localization is not just only there are 10 humans, but this is where they are, right, in the picture. So that's the methodology we use for the first, computer vision techniques of object detection and localization. We can detect not just only we're looking at an entire length of pipeline, but again, within the pipeline, what segments are, are there, those corrosion defects. Then the second part we took was the instance segmentation. Actually, before instance segmentation, there's also what they call semantic segmentation. But why we moved with instance segmentation is that with instance segmentation, one is that you're actually classifying and localizing where the objects are. But additionally, to you're now attributing those classification to the pixel intensity. So this just gives you like, a snapshot of, all what I alluded earlier. So you can see for this, you can be able to detect, actually like on the image on the extreme, the two uniform corrosion images, you can be able to detect, what areas within that segment of your pipeline that you're experiencing, such type of corrosion. Similarly too, for your stress corrosion cracking, you can be able to like, pick out what area of it, so you can detect multiple corrosion types on the pipeline by their locations. For instance segmentation, just giving you a sense of instance segmentation. So now it's not just only that you're detecting the location, but now taking it further step, the pixel intensity. To determine the pixel intensity of the different corrosion types. And so yeah, based on that, you can identify multiple corrosion types, at their pixel level. Now so what I just shared was the computer vision techniques, but obviously, like I alluded earlier, you want to, it gets to the point where these features or this corrosion defects are irregular, right? So you need something like a network, like the convolutional neural network that can handle that, non-linearity in your sets of features. So for the two papers we worked on, for the ResNet, so we use what they call like the ResNet. So ResNet is just an extension, an enhanced version of your typical convolutional neural networks. How the ResNet came into place is from your convolutional neural network. If some of us are conversant with what they call exploding gradients. So from exploding gradients and from degradation of the accuracy of your features, that the ResNet convolutional neural network came about. Well, however, what the ResNet does for you is primarily extracting the features, generating feature maps from your first input before you can now pass it into like other subsequent layers and subsequent layers and subsequent layers of your neural network. As far as for the object detection and localization tasks we did, we use what they call a faster RCNN model. While the faster RCNN is a lot more better, is in terms of accuracy for critical systems of corrosion defects. You want to, as much as possible, detect accurately. Then similarly too, for instance segmentation, you're just basically being able to segment, detect base pixel level of it. This just gives you a sense of feel of what I alluded earlier. So the faster RCNN, talking about generating the feature maps from the convolutional layers. Then also at the other end of the network, where they call the region proposal network, where you generate the proposals for your regions of interest. So this just gives you a snapshot, of what the masked RCNN entails. I'll try as much as possible, to move fast. You can always, I'll share the references where you can, go and look more into the paper. Then just give you a sense of feel of the results from the object detection workflow. So this is just a feel of like the original image and the results that were obtained from it. Similarly too for the instance segmentation as well. So similarly to the same, the results for object detection, workflow, and as well as for instance segmentation. Last but not least, for conclusion, in every model, or both the instance segmentation and the object detection computer vision technique, what we're always trying to do is strike a balance between speed and accuracy. So obviously if you want to improve your model accuracy, you want to be, I mean, you need to be cognizant of the fact that maybe you might, err on the speed side. And as a matter of fact, all the advances in, convolutional neural network to the ResNet to from faster RCNN, or all kind of, convolutional neural network has mainly been on extraction of features. So once you're able to extract the features more, the more accurate your models become. Another challenge too, like I alluded earlier about limited data, some of that too with current research in the computer vision space, using something like what they call a generative adversarial networks, you can be able to, solve that problem. Then last but not the least, when I talked about like the challenges with the model training, having something like a distributed file system where you already have the data that you want to train your model on loaded in memory, it makes it a lot more quicker for you to iterate and solve more greater problems. Thank you. And yeah, if you have any questions, feel free to reach out. And I'll make this slide available, so if you want to go, look at the reference for the 2 SPE papers I talked about to give you more, detailed feel of, what our work, what it entailed, that would be good. Sure.
Thank you for that presentation. The floor is open for any questions. Okay, thank you for that presentation. I'd like to give you a small bit.
Thanks for sample this.
Thank you, CJ, for
Yeah.
coming here.
My pleasure.
Oh,
Oh, sure.